Hi, today we will be discussing about metamaterials. It's a very small introduction that is included in this particular course. So we won't be spending too long on this because this is a very involved subject in itself. However, we will have a flavor of what metamaterials are and how it fits into our nanophotonics course. So in nanophotonics so far, whatever we have discussed, one can say that we are talking of light matter interaction, and in this perspective the way we see things are that light is considered to be it is an electromagnetic radiation. So the properties of matter which define this sort of interaction is basically there is epsilon, which is the dielectric constant, which decides your response to electric field of the electromagnetic wave. And mu, in our case, mu is nothing but the relative permeability of the material, and mu is defines the response to the magnetic field, response of the system to the magnetic field. Okay, and so far before till now we always considered mu to be 1. So the material is non-magnetic, and so the permeability is given by mu naught. So mu becomes 1, but now we will see that for metamaterials particularly we need to have magnetic materials. Before why I brought this up here, because in all these explanations and the topics that we had covered in this course, we talked about epsilon, and we talked about how one can modify this epsilon. So whether we make it into a photonic crystal or we make it into a confined structure, push it towards quantum wells or quantum dots, we are changing the optical responses, which in turn can be related to the change in the dielectric constant. So this is exactly what we will be doing again, and that's why metamaterials is a part of our nanophotonics course. So nanophotonics actually encompasses all the processes in which one can modify the dielectric constant, and the relative permeability, which eventually points out to a change in the optical response of the system. So how do we see the thing here? Let's start off now. So let's say it's a very schematic way that we are trying to do. So let's say this is epsilon and this is mu. Please note that the imaginary part of these are always positive, because that will lead to certain sort of attenuation. At least for passive materials, imaginary parts have to be positive. If they are negative, then it will show some gain in the system, which is not what happens in a passive system. So here by epsilon and mu we mean the real part of epsilon and mu. And so we have these 4 quadrants. So in this first quadrant we have epsilon greater than 0, so epsilon is positive and mu is positive. This is typically what we have seen so far in case of dielectrics. Okay, and in dielectrics we know the electromagnetic wave or the light can propagate, so we have propagation. Now in the left side, the second quadrant, in this section we have mu is positive, however epsilon becomes negative. So this type of material, where did we see it? So mu positive, mu is 1, and so on. Epsilon negative, this happens when we talk of metals, or may also, for example, in case of a highly doped semiconductor. So we are talking of conducting systems. So in case of metals, typically for omegas less than omega p, so that also it has to be less than omega p. This is the domain I am talking of, because for omegas greater than omega p, a metal starts to behave as a dielectric. So in this regime, when the metal looks like a metal the way we know metals, or also in case of a very highly doped semiconductor, this would be the region where epsilon is negative while mu will be positive. And this is where we know that we have already seen and discussed, we have evanescent waves. Or rather evanescent fields. Now then we come to this other quadrant. Here it's also quite this thing, epsilon is positive while mu will be negative. This happens for magnetic materials, can happen. Typically, let's say we can think of ferrites and so on. This also is a place where we will eventually we will have evanescent waves. So it's quite similar. Evanescent fields. So this is nothing but like a magnetic plasma, where we have negative mu but a positive epsilon. So we are left with the fourth quadrant. The fourth quadrant will have both of these negative. Epsilon should be less than 0. Sorry. Epsilon is less than 0 and mu is also, both of them are negative. This is a very special case, and this is not naturally occurring. So far we have not found any material in any frequency regime where both of these get to 0. So these are not naturally occurring systems. So one has to make them, and this is where we have our metamaterials. So metamaterials are materials which has both epsilon and mu to be negative. And what does that imply? That will imply, as we will see later on, that the refractive index n will be negative, will also be less than 0. This is called negative refractive index material. So we can, from now on, this we will call as NRI. Okay, so this is the region of our interest, and why is it interesting, or why this has led to a certain new field of work and research. That's what we'll be coming to. So what are the implications? So we said that if we can just make it a little more systematic, we said that for metamaterials we have epsilon negative and mu also negative, which implies that n is also negative. Okay, implies how, we'll come to that. But first we say, okay, let's say n is refractive index is negative, or either or mu and epsilon are negative, then what does it tell me? Why is it so interesting? So let's get back to this. So we are talking again of light matter interaction. So we have the electromagnetic field for the electromagnetic radiation. So we can write E, a plane wave, let's say, is exactly what we write all the time, k dot r minus omega t, right? So this is what we have is the electric field, and similarly the corresponding magnetic field can also be written in this form for the electromagnetic radiation, the light that is incident at a frequency omega. So now with this in mind, of course we know the Maxwell's equation. So curl of E is minus this, and so we can write it as this. So if this is the case, consider the curl. Curl is like a space operator, right? So if we do curl of E, this is nothing but, because only the spatial dependence comes from k dot r, this term. So what we have is ik cross E. This is your derivative with respect to space, and with respect to time, as we have always done, it is minus I omega, and this is H. So this is what we have. So right hand side, if you remove the i's and the negative sign and everything, k cross E becomes mu omega h. So this is the first relation we have, the relation between E and H. Similarly, one can do the same thing in case of curl of H, which is the displacement, partial derivative of the displacement vector. Just mind it that there is no negative sign here, so there is a sign difference compared to the previous one, and we'll do exactly the same thing. Curl of H then turns out to be I k cross H, and on this side I have I omega epsilon E. So k cross H minus epsilon omega E. They're all self-consistent. I mean, both work out together. That's not a problem. So now what we do is, so with this in mind, what the next step would be that let's look into the pointing vector. Okay, so this is something we all are familiar with. Pointing vector S, right? It is equal to, it is typically given by half real part of E cross H. So what does pointing vector tell us? Pointing vector tells us the direction of flow of energy of the electromagnetic field. So all we do is we either can, like it has E and H both. So either we can replace H by E or E by H and get it into one form of either S as a function of E or S as a function of H. So let's do the former. We replace, so from this relation, as you have seen here in this relation, we can write H is nothing but K cross E by mu omega. So if we substitute it here, then the S vector becomes half real part of E cross K cross E by mu omega. Okay, so how do we get further into this? So we know the vector identity. So we have A cross B cross C, if you remember from your early vector analysis courses. A cross B cross C, it becomes B into A dot C minus C into A dot B. So in our case, E cross K cross E becomes K E square minus E K dot E. Now K dot E for a transverse wave, this is equal to 0. So we are left with K E square. So once we substitute that, what we find is S is equal to half real E square mu omega vector K. Okay. Now in this relation, so we have this, and now let us consider. So this is what we consider for normal. So for normal materials, the ones generally normal materials. By normal, I mean they are not metamaterials. We have epsilon is greater than 0, mu is greater than 0. So this is all positive. These are all positive numbers. And so what happens is AS is along K. However, for metamaterials, the system of our interest, we have mu is less than 0, mu is negative. So in that case, we will find that S is along minus K. That means that the pointing vector goes in the opposite direction. So energy flows opposite to K. So this is very counterintuitive. However, this is what happens for metamaterials, and if you want, there are a lot of simulations and plots online, so you can check, and there are lovely videos which will visualize that the K vector, the wave fronts, they move in one direction while the whole package of energy moves in the opposite direction. And this happens within the metamaterials only if you have a negative refractive index material. This is where I stop today, and will continue in the next lecture. Thank you.